إذا يعني في السيمينار إذا في أي أسئلة ممكن أنكم ترسلوا بالتشات، ولا في نهاية السيمينار يمكن أيضا نتواصل صوتيا. So greetings to everyone, and by the end of seminars, if you have any question by written question, or we can also discuss directly together. So Dr. Aid will arrange this. And today I will speak about spectropolarimetry as a new diagnostic window on the sun's hidden magnetism. New in the sense that it is something which now becomes more and more popular. And I will start by defining or explaining what it is, the spectropolarimetry. So the spectropolarimetry, to understand better what it is, the spectropolarimetry, and then what it is, the second solar spectrum, I will start by something that every one of us might know in principle, is the spectroscopy. Spectroscopy is the analysis of radiation emitted or absorbed by by any astrophysical medium. And here, for instance, it is the spectrum of the sun, mainly in the visible part of the sun, and those invisible lines which are in black are absorption lines. So this is the absorption spectrum, or also called Fraunhofer spectrum of the sun. So the study of this spectrum gives a lot of information, but in general, we want more and more information. And if the technological development allow this, it will be very good. So by this development of a new generation of accurate polarimeters or spectropolarimeters, it was possible to observe polarization which is very, very small. The possibility is can go to observing something which is about 10 to the minus 4. And that means that the polarization, even if it is very small, one can observe it with a very good noise, signal to noise ratio, in the sense that the noises will be very, very small compared to the signal. And that was possible only by the end of the 1919th and the beginning of this 21st century. So this is very modern and very new field of research. Let's, since we are speaking about spectropolarimetry and we are speaking about Stokes I, here are the Stokes I, Q, U, and V, which are the 4 Stokes parameters. I will just give a very quick description of this. So the polarization, or the polarimetry, which is the measurement of the polarization, quantifies the orientation of the electric field. The electric field is one of the fields which characterize the electromagnetic radiation. So we have electric and magnetic radiation, and by convention, one describe in general the electric field, but it is equivalent to describe also the magnetic field for the polarization diagnostics. So here the light is colored to be polarized if the electric field has a privileged direction. And then the state of the light must be described at least by 4 Stokes parameters. So the intensity only is enabled to give the whole information about the light. One needs to include other 3 parameters. Q and U are associated to the, so Q and U are associated to the linear polarization. However, VR is associated to the, which called circular polarization, and I is the intensity, al-kathaf. Polarization in Arabic is al-istiqtab. Here the light is called to be unpolarized if the direction here everywhere is the same. I mean, we have the same intensity everywhere, so there is no privileged direction. And then we have zero polarization here. And if we put a polarizing filter, for instance, we can select one direction to give some privilege to that direction, and we get a polarized light here. The idea of polarization means that we are breaking some symmetry here everywhere. We have the same orientation and same parameters everywhere. The space is equivalent. There is a perfect isotropy of the space. We can break this isotropy by the fact that we put a filter. So we give privilege to this direction, and then we get only one component, and thus the light becomes polarized. So here, the one of the most important application of the polarimetry is the solar magnetometry, or also it is kind of the art of measuring magnetic field maps in solar atmosphere. Not only in solar atmosphere, it can be also applied, and currently it is applied in circumstellar medium. It is also in the atmosphere of Jupiter. In the Earth's upper atmosphere, we have this oxygen lines. So this is kind of field which is really in emergence now. It becomes more and more important, this kind of diagnostics based on polarization of the light. So it is kind of, you are going from the case where you have only one set of data based on the intensity alone to 4 sets of data where you have the intensity plus the polarization. The polarization itself has 3 Stokes parameters. The whole number of Stokes parameters is 4. So if you have more data, you will, when you interpret that data, you will get more information, which is in principle was inaccessible without the polarization. So the polarization will open a new window, or kind of the whole door, to see what it is in many atmospheres of stellar atmospheres, or galaxies, and the circumstellar medium, or in some planets where there is any breaking of the symmetry, where there is any polarization. You can apply the polarimetry to get a lot of information. And here we use the word art. Why? Because since the field is in emergence, so everyone puts some many ideas going together, and each idea, it is a kind of different look to the problem. So the now what we can also okay, I have been informed that maybe was not it has some problems in the connection. Hope that now you are hearing me better. Now it is okay. So yeah, now I because I changed the network actually. So here is an example of what it is, the importance of the polarization. Here it is a map of the atmosphere. What we can see here in red or in blue, which, and here we put a zoom on it. What we see here is the orientation of magnetic fields. And the magnetic field is the main player in the sun. The dynamics and the structure of the sun are mainly governed by the magnetic field. So, but this information is also gives a part of the real information, because what it is in gray, it is a hidden energy of the sun. So we can just detect, without the polarization, we can only detect those magnetic fields. The rest of which is in gray is impossible to detect without the use and the help of the polarization. That's why the polarization here is very important, a very important tool. Of course, there are many good reasons to study the sun with the polarization as a tool, and I give here four reasons which I think are important to cite. The first one is knowing the sun. It permits us to predict changes in our environment caused by the activity of the sun. So everything around us is based on the activity of the sun. The Earth is a closed system, and the only, almost speaking in practice, or the only source of energy from outside is mainly the sun. So it is important to predict this kind of energy and the changes. Also the conversion of the sunlight into the solar energy, and also I can cite also the fact that the sun is a very nice and very important natural laboratory. So when you are studying the sun, it is a very good opportunity to apply the laws that we learn in atomic physics, in quantum mechanics, in molecular physics, in the hyperfine structure effects, which are very small effects, can be studied by observing the sun. So they are very small effects when we look to the energy or to the differences in wavelengths are in the order of 1 or 2 angstrom in wavelength point of view, but can be seen and observed clearly in the sun with this modern generation of telescopes. Of course, the sun can be used as a sample because it is about 270,000 times closer to the Proxima Centauri, which is the closest star to us. And then studying the sun gives very nice idea about the sun-like stars, which are very frequent in the cosmos. Here, I will give some overview on the sun and its structure before starting the second solar spectrum case. We have the nuclear core, where it is called nuclear because the nuclear reactions happen here. And then you have the radiative and convective zone. And after that, we have this is the anterior part, of course. Then the atmosphere, or the exterior part, it is composed from the photosphere, the chromosphere, and the corona. What we see, of course, when we are speaking about the solar disk, we are speaking about the radiation coming from the photosphere. Here it is a good example of the solar activity. It is this observed by the extreme ultraviolet imager imaging telescope, which is on Seoul satellite, and this satellite was launched in December 1996, and at that time it was the first observations to this iron line, and we see that at that time we have the minimum of activity of the sun. And then this is the cycle 23. Then we see that the activity starts to be there 3 years after, and the maximum of the activity, it was about 2001 and 2002. This is the maximum of activity. So we can see here the solar cycle is very clear in this observation. There is another idea that I want to present here, the fact that we can observe different regions of the solar atmosphere, or the stellar atmosphere. What we say for the sun is also very useful for the other stars. So here we are speaking about observing different regions. Observing different regions is equivalent to observe different wavelengths, because each wavelength is formed in different place or in different region in the sun. Now, I think here I have to say something which is very important in the topic of solar physics, and in this topic of research. The good thing for the solar physics is that the data is available. The observations, very accurate observations, are available. And here I give an example of some observation observed. Today we are November 4th, so it was observed something like 25 days ago. They are very recent observation and are already there, and they are given in different levels of study. So in level 1 are the FITS files, they are observed, and level 2, for instance, are something with some very preliminary analysis. So anyone can get the very nice and very accurate data and do very good research in very high level, even if we don't have a telescope, even if we are living in in our countries, for example, we can do very good research by modeling cases, and by theory, and by helping people who give this kind of very nice and very accurate observation available to us. Now, the famous second solar spectrum, الطيف الثاني للشمس. The word second here means that there is a first. The first is the ordinary spectrum, the normal spectrum, which is the intensity spectrum. When we say spectrum, we are speaking, the y-axis is the intensity, the x-axis is the wavelength or the frequency. So here we are speaking about the second solar spectrum, in the sense that it is different from the first spectrum. And the second solar spectrum, it is a word given by a Russian scientist in 1991, and it was for the first time given in this time at that year, but it was started to be used almost 5 years after that, 1996 or by the end of 1995. We started to see the first publication using the word second solar spectrum. Before that time, second solar spectrum as a term was not used in the literature, in the publications. So, well, it is by Ivanov who was the first one, but who gave the name. But the first observations and results were mainly given by scientists like Egidio Landi, Deglin Nishinti, like Jan Stamflu in Switzerland, and some groups in United States. So, and then they started to give results for and publication. The first atlas with hundreds of lines were observed by Akim Gandorfer, who is working currently in Max Planck, and he was a student of Jan Stamflo. And this spectrum is available in electronic version and also in books. There are 3 books with 4 different ranges. So we have all these observation as numbers. So it is a huge number of data. If one can analyze this data, there is very nice science and research to do with this kind of data, which is available, and I have it in electronic version actually. Now, how this spectrum was formed? The spectrum, I will explain on it and come back on the explanation again after in some other slides. This spectrum was formed by a break again by breaking of symmetry. When we are speaking about polarization, الاستقطاب حتى بالعربي يعني even in Arabic meaning, it means that we are putting the way of thinking of people or any process on one line or one privileged line or one privileged direction. So here the breaking of the symmetry is in the sense that we imagine that the observed atom or molecule is here in the photosphere. This yellow thing is the sun. So here we have an atom or a molecule. This atom or molecule is excited by light which is coming from the center and light which is coming from the limb of the sun, from those directions. So we can demonstrate it with some small number of radiative transfer equations, that the radiation coming from here will be much smaller than the radiation coming from here. And then this is something which will be seen by the atom. So the atom will be excited by light which is large in the center and small in the limb. So there is kind of anisotropy. So the anisotropy means it is breaking of the spherical symmetry. The breaking of spherical symmetry will result on some polarization of the atom itself. And when the atom, after excitation, when the atom will be sending to us light of excitation and then de-excitation. So this process will result on emission of light. So this light will be polarized, and the polarized light is called second solar spectrum. By quantum mechanics and scattering physics effects, one can demonstrate that in this case, in this precise case, the light has to be linear, cannot be circular. But sometimes in some other contexts, also the circular polarization can be formed. But the second solar spectrum is only linear polarization spectrum. This second solar spectrum, when I was speaking about the hidden magnetic field, in the sense that the second solar spectrum will reveal to us, will give to us the key to see and to open the door and see by very accurate way that there is in the quiet sun there is a small magnetic field, but it is everywhere because the quiet sun, as a surface point of view, is a majority in the sun. So we can see the maximum of magnetic field on the quiet sun, and the magnetic field has an effect on the second solar spectrum. So this effect is a kind of a signature. So when we look to second solar spectrum, we can see a kind of signature, and this signature is the signature of the magnetic field. So when we analyze the second solar spectrum, we can obtain all the hidden magnetic field, because it is the only way to see that magnetic field of the quiet sun. Previously, one gets zero, so there is no energy, no magnetic energy. The magnetic energy was hidden, مخفية غير مرئية, when we don't use the second solar spectrum, and which is and the Hanley effect of the magnetic field. So the Hanley effect is characterized by the variation of the degree of and the direction of the second solar spectrum, or the linear polarization spectrum. So just to concentrate on that and this idea, we have the magnetic field. The magnetic field will make some variation of the second solar spectrum. This variation is a kind of signature of the magnetic field, or fingerprint of the magnetic field. So from that signature, we get the small magnetic field. This signature is visible only on the second solar spectrum. So if we don't observe this second solar spectrum, we cannot see or we cannot determine the magnetic field. And those are the different ranges of magnetic field. So we can see a magnetic field which is 5 over 100,000 by Gauss, which is extremely small magnetic field, and it can go till 258, for instance, magnetic field. So in Gauss, of course. Here is a table which gives different magnetic field which can be observed. For instance, this magnetic field, which is 295 Gauss, is not observed without the second solar spectrum analysis. And we have the second solar spectrum. Now, the main problem is the analysis, is the theoretical analysis. And theoretical analysis can be done just by computer and by a good way of taking things correctly in theoretical point of view. Here I will go to more and more deep to the way of thinking of the second solar spectrum. Let's go do kind of resume of what I was saying. Center to limb darkening means that the intensity coming from the center is larger than the intensity coming from the limb. It is what I was showing here. I will go back just. It is what I was showing here. This is the center to limb darkening. يعني وكأنه من المركز إلى الأطراف الانتنسيتي أو الضوء، كمية الضوء تنخفض، فبنقول بيسمى center to limb darkening. So we have the center to limb darkening, or some atmospheric inhomogeneities like the active regions, which for instance the sunspots, they have smaller quantity of light than the quiet sun, so it is a kind of a breaking of symmetry. Any breaking of symmetry, أي شيء ليس فيه تماثل. So if we have this center to limb darkening or any other geometrical effects or any atmospheric inhomogeneities, that means that we'll have kind of anisotropic elimination or excitation of atoms or molecules, and this will result on some creation of atom, which is called atomic polarization. Atomic polarization ولا atomic order ولا organization, this is kind of a way of saying that instead of having the number of electron similar everywhere. For instance, here in principle we'll have 6, 6, 6. In this case, there is no polarization. But if we see that here, for instance, the number of electrons is smaller than the other level, the other levels, one can say, okay, there is kind of order, a way of organizing things. It is like when you have, in principle, first floor is in principle full, and then second floor and third, fourth floor, and so on. So, but in some, for some reason, you will see that the first floor is full of people in their flats, and then the second is empty, and then we go directly to the third floor, and the second is empty for some reason. So this may make some polarization. So the polarization means that we don't see the same thing everywhere. So here the atom is polarized, and this polarization is called atomic polarization. And this order, or this polarization, will be transferred from the atoms to the emitted light. And since the elimination or excitation, it is a kind of scattering, it is a kind of interaction between an atom and the light. So we are speaking about scattering polarization, or polarization formed by scattering. And here, this interpretation of what is happening here in 1 and 2 gives the result about the kind of weak magnetic field in the quiet sun, the velocity also, because when if the atom is moving, the polarization will not be the same, quantum coherences and hyperfine structure, radiative transfer effects, very important collision effects. All of those can be seen in the by analyzing what is happening in 1 and 2, in steps 1 and 2. And again, the observation of those phenomena are available. What is happening here is observed. It's not something that we are just thinking that might will happen. It is something which is observed, and the models are fit very well with the observation. Well, here just to explain more things. So, for instance, for J equals 1/2, J is the momentum. This difference of population results on which is called orientation of the level, and it is the linear circular polarization here. And here also we can show that in this configuration, in this way, we'll see the linear polarization. And for this organization, we'll see circular plus linear together. Now there is also, which is associated to what I am showing here, there is also another concept, is the density matrix concept, which is in general we describe which is happening here. We describe it by the wave function psi in quantum mechanics. Is very well known as a concept. So this will be replaced by the density matrix. Why? Because this is enabled to describe the huge number of atoms. So this will describe only one atom. So that's why we introduce the density matrix. Formalism, and we write the equations, we add all the processes, collisions, radiation, magnetic field, all the processes, and in the statistical equilibrium cases are equal to 0. And this is a way on, or has to be coded. There is numerical codes, not very complicated, and also are available even in the literature. One can find those kind of codes. We have this kind of codes in our department. So to solve those equations, to obtain the density matrix elements, if you obtain the density matrix elements, you obtain what it is happening inside the atom, and then you determine the second solar spectrum. So again here I can show some observation on C2. This is a molecule. So in the sun also there are molecules, and we have obtained for the first time results on the CN molecule. It was never obtained before, and we published this year a paper on CN with Dr. Saleh Kutub. And here also an observation on the which is observed in the Pic du Midi in France, but there are observations which more accurate in Timis, also in Canary Islands. There are other observations in Ascona by Zempol in Timis in Switzerland. There are other observations in Colorado, in Achao, in United States. And these, for instance, demonstration on how the polarization will be smaller and smaller when we are going from the limb to the center, because it is a kind of decrease of the polarization. Why? Because the source of the polarization will decrease. If the anisotropy decreases, the center to limb decreases. If we are going from the limb to the center to limb darkening will decrease, and then the polarization will decrease. This is also another slide to show what we done to fit the spectrum of this line, the strontium line for 4607 angstrom. This is very famous line, and we get the magnetic field about 46 Gauss. And it was one of the first determination of the magnetic field in the quiet sun. So we have 46 Gauss instead of 0. It was hidden before. It was not known at all, and it was believed to be 0. So here, by interpreting the polarization spectrum, here we are showing the intensity and polarization. So we fit them together, which is in red here are the results of the theory, and which is in black is the observation. So black vs red, and once we obtain perfect or very good agreement, we can extract the value of the magnetic field, and it was at that time about 46. Here I was speaking also about the hyperfine structure. We can see them. This is an observation of the hyperfine structure, which is done by Jan Stanflu. So we can see a peak. This line is this one, and we see this line and the principal component of the line. So we can see 3 of those lines, which are coming from the hyperfine structure. In principle, if we don't have a good resolution, we'll see only one line. But I am giving those examples not in very deep details, but just to show that even in the sun we can see different the hyperfine structure. The name hyperfine means that it is extremely fine. It's very, very small. And even with this small thing, we can see it. This is also another observation, mainly for the titanium, which is a complex atom with very important spectrum. If the atom is complex, that means we can it has a rich spectrum, and the modeling is difficult, but it has a good number of information. Now, when I was speaking about the collisions, it is in the sense that the collisions play a role when they are the rates of collision are about 1 over tau. Tau here is the life duration of the level. It means that the time that the electron will pass on the level. So if you have the collision rates, you can get the magnetic field with better precision, and it is something which we proved it before when we were speaking about this barium line, for instance, and we showed that by neglecting the collisions, our magnetic field, the error bar on the magnetic field is about 35% in the chromosphere, where the density of hydrogen is 210 to the 14 per centimeter cube. So in this density, which is typical to the chromosphere, people think that the barium 2 is formed without the collisions, one can neglect the collision with hydrogen, but we determined the collisions and we determined the polarization with and without that collisions, and we determined the magnetic field with and without collisions, and we showed that there is an error bar of about 35%. So that means collisions is very important. And almost now in the world, the collisions are the depolarizing collision. I'm saying clearly the depolarization or polarization by collisions is worked mainly now in our department. It is there is very few people in the world who are working about this subject, but it is very important subject, because if you are doing accurate measurement of polarization and you lose that accuracy just because you don't know the collision rates, this is very unfortunate, because then you will obtain inaccurate magnetic field. So this also I will go more quickly because I don't have a lot of time, but this is mainly our work of collision. This is an extension, because when I was speaking about the titanium is a complex atom. So it is a complex atom. So it has a very good spectrum of polarization. But the collisions of this atom with hydrogen are not known until we extended this theory that we developed, myself and Sahal Brisho and Paul Barklem. We developed it for simple atoms, and then we extended it to complex atoms, and we published different papers to explain how this extension was done, and it was for the first time that collision rates for those complex atoms were calculated. And until now, it is the unique determination of these collision rates which has been done. Also, we proposed some hybrid way to determine these collision rates. I am showing this just to say what it is going on in our department as work to explain this kind of interesting problems, and to contribute efficiently to solving the secrets of the second solar spectrum, because as I said, the observations are there. We have even an electronic version of all the polarization degrees for all lines. So now the main work is on this kind of analysis. So for instance, we have for this strontium line that I was discussing before, we have different determination of collision rates. And recently, in the last year, we determined the most accurate rates, which by using a kind of hybrid approach. Hybrid approach, we mixed the quantum approach with the perturbation approach, which is also has a kind of semi-classical aspect. So we mixed them, and we obtain a kind of hybrid approach, which gives the best and the most accurate rates. So That was an improvement, even if of work that I was published in 2003 and other quantum chemistry works published after that time. And the last year we reviewed this and we published this in Astrophysical Journal. Also, as I said, for the first time, we published the rates for this for the CN. CN molecule has very important and very nice second stellar spectrum. Important in the sense that it is very complicated and has a lot of nice structure. So, the enigma, allows the thing which was not known is the collisional rates. So we started for the first time. I am saying there is no any other result which has been done before our work, and we obtained the depolarization rates for this. And the main author was Dr. Salah Qutb, and this was published recently in Mineras. So, and this is for the ground state. Now we are working to obtain this for the excited state, because as you know, the transition or the line, it is between ground and excited state. So to have the complete information, we need to determine this for both states. And this is in collaboration with the Russian and the French groups. Those are the rates that we published already. And also we tried to give some unified result, in the sense that we generalized our results and gave variation laws to be used easily in the modeling cases by other groups. Now, for the magnetic field, as I said, we obtained the magnetic field, which is about, here for this observation, it was between 30 and 40 Gauss. It depends on the region, of course, of the observation, but it is in general some tens of Gauss, and it was neglected before. The magnetic field also was obtained by analyzing the barium-2 line, and here it was by analyzing the strontium line. Of course, the barium-2 is formed a bit higher. It is a chromospheric line, so the magnetic field is a bit smaller. And we also gave results for the coronal magnetic field for Lyman alpha in the sense that to prove that this line will be very interesting to observe in the future. Of course, this is kind of work to encourage people who are working in observation to observe some good candidates of lines. Here we are including different models of magnetic fields and see what will be the Hanley effect. Now here with zero magnetic field, B equals to 0, and here dipolar magnetic field, and here dipolar magnetic field with some equatorial current shift, like what can be happening in the sun. We also added the effect of the of plage of plages and sunspots, and we see that plages can decrease this is the rotation angle. It goes to negative rotation angle. Sunspots will rotate the polarization plane, but to the positive direction. And here the effect on the polarization is almost the same. We are speaking about similar surfaces of plages and sunspots. Here, what I was speaking about for the second solar spectrum is scattering polarization, but there is also, I will mention it, by the presence of a strong magnetic field in active regions. And here, for instance, it was George Heil in 1908, more than 100 years ago. We observed that when he puts the slit of the telescope inside the sunspot, there is a split of lines, and this split is a Zeeman effect, and there will be give emergence to two lines, circularly polarized line and linearly polarized lines. I will finish this part of magnetic fields by this slide, in the sense that we were developing the numerical code, and we use a known input. So we have something that we know already, and we put it in the code to generate the polarization, and then we took that polarization to retrieve it. In the perfect case, what we retrieve is perfectly equal to what we put. The input and the output should be the same, and we are working to put those things as similar as possible. This is for longitudinal component, and this is for transverse component of the magnetic field. So our aim was to show how is the precision of what we are doing by using something which is by using a known solution. الحل بنعرفه already ونحاول إننا نجيله مرة ثانية. We use known solution to retrieve it again. This is also something which was in comparison with Merlin inversion code, which is an American numerical code, with our code, and we find in principle the two codes, if they were very different, the results will be here or here. But since they are around the x equals to y result, that means that the two codes gives similar results. Again, we done this for different regions of the sun. So we have a quiet sun, Plage, Penumbra, and Umbra. What is next? I put here some different projects about the impact polarization by collisions, coronal polarization, and the effect of the active regions. Going more and more in those molecules. For C2, for instance, we have 0 results. For Cn, we started to give, as I said, the ground state. And for the MGH, we have preliminary results, but not published yet. We also we want also to undertake the case where the collisions are happen in the presence of magnetic field, strong magnetic field, and this is very new topic. It was not done before. So before I thank you for your attention, and I would like to thank all those people. Without them, I would not be able to show what I was showing today. Those are people that mainly I collaborated with them to present the results that I am presenting today. I am not putting all the list of collaborators, but the main collaborator that gave me the opportunity to work on what I was presenting today. Thank you very much. And I am open to any question by chat or by directly discussing with you. Dr. Ayb?
Thank you very much, Dr. Munsif, for your interesting lecture. Now we are opening the questions. If anyone has a question, and if anyone wants to communicate verbally, so we'll take the first question from the chat from Lama Mansour. Dr. Munsif, has any second solar spectrum-like behavior been observed in stars other than the sun?
Yes. Well, if it is observed in other, let's say in other stars, will not be called second solar spectrum, but it will be scattering spectrum, and there is It is observed in Jupiter, in the circumstellar medium, and for the stars, maybe in next years, the precision will be better and we'll be able to observe this. In general, it is easier to observe anything from the sun because, of course, the magnitude of the light of the sun, but it will be coming. I mean, because what it is happening in the sun, it should be similar for the other stars. But for the moment, we have observation in the Earth atmosphere. We have observation in Jupiter and observation in circumstellar media and in some galactic regions.
And are any other studies were published in scientific journals?
There are publications for those examples that I have said.
Okay.
If she is interested, I can send her some of those publications.
Okay. So we'll take mute from Amal Salim Al-Garni. So Amal, go ahead. Yes, Amal, you can ask your question.